these are difficult examples, and I'm going to do another example of using integration to be able to find the volume of a geometric solid. So this is an even crazier shape that we're going to try to find the volume of. Suppose we have a tent with a footprint, meaning that the bottom of the tent has the function y minus x squared in quadrants 1 and 2, so just the positive part of this parabola. And the heights of the tent are isosceles triangles with height values of half of the base length. So I'm going to draw a picture of my interpretation of this. So the base length is this length down here, which in this case is exactly x, right? My x quantity is right here, and that's going to be what the height is at any given point. So my tent is going to look something like this. It's going to be built out of these triangular regions. And as you go along, my base values here get shorter and shorter. And that means that my heights are going to get less and less. And my tent is going to curve downwards with a peak up at the top becoming 0 down here as my tiny triangles have height 0. So the idea here is that I need to now find the volume of this tent. Let's look at our slices of our bread. So our slices of bread are each going to be these triangle-shaped figures, and my first question is, what are the bounds? Let me use a different pen. And that's asking sort of, how many slices of bread do I have? Where do my slices of bread start, and where do they stop? And I can see, looking at the footprint, so looking at the base of this figure, it starts at a y value of x equals 0, and then it's going to extend up until this intercept up here, and given this function, that's when x equals 0 is going to be where y equals 9. So I know my slices of bread go from y equals 0 to y equals 9. But the next question is, what's the area of each slice of bread? Well, let's look at each slice of bread. Each slice of bread is going to be a triangle. And what's the area of a triangle? The area of a triangle is going to be 1/2 base times height. And we need to put each of these variables in terms of our variable y, because when we integrate only with respect to y. We can't have all these extra variables floating around here. But one of the pieces of information that we have looking at these triangles is that I can see that from this picture, half of this length right here is exactly equal to the height, right? That was given in the problem. And that I can measure this by the width of this here is really just measuring my x values, as my x values get shorter and shorter as the y values increase. So this is a really quick way of saying, oh, this piece right here is length x, this piece right here is also length x, and this height right here is the same as half of the base, which is also a value of x. So I could rewrite this as 1/2, in this case the base is 2x, and the height is x. But we need a way to be able to relate our x, this function, to our y function, and this is the hard part. Need a function to relate x to y. Thankfully, unlike the cone example that we did previously, in this example, we're given an explicit formula that relates our value of y to our value of x. We know, in fact, that y is equal to 9 minus x squared. I can solve for x, and I get the fact that y minus 9 is equal to negative x squared. So that means that 9 minus y is equal to x squared. and I'm going to square root this function, noting that square roots are not one-to-one operations, so this isn't the inverse, but we're only dealing with positive values, so I don't have to deal with the plus or minus thing. Why is this helpful? Now I can go back to the area of the slice of bread and, now I can go back to the area of a slice of bread and rewrite it in terms of y. So my final step, maybe I'll say that thus each slice of bread, when I say slice of bread, I actually mean these triangles, has area of 1/2 base times height, or 1/2 of 2x times x, and rewriting that in y language, that's going to be 1/2 of 2 times, well, what's x? The square root of 9 minus y, times x, which is the square root of 9 minus y. Thankfully, this ends up being a rather straightforward integration problem now. So we found before, let's set up our integral. Our integral, I'm going to add up, where does my bread start? It starts at y equals 0 and it ends at y equals 9, because that's the base of the footprint of this tent. And I know that the area of each slice of bread is going to be the area of each of these triangles, and we found that the area of each of those triangles is going to be 1/2 of 2 times the square root of 9 minus y times the square root of 9 minus y. Again, where did this square root of 9 minus y come from? That's the formula that was given in the problem that relates x's and y's, and we needed to rewrite 1/2 base times height of each triangle in terms of y. So this is the area of each slice of bread, and our differential dy sort of tells you the width of each slice of bread to get the total volume. And the nice thing is that this simplifies nicely. 1/2 times 2 is 1, and square root of 9 minus y times square root of 9 minus y is just 9 minus y. So this is the integral from 0 to 9 of 9 minus y dy. Easy to integrate. That ends up being 9y minus 1/2 y squared, evaluated from 0 to 9. Plugging in the upper bound, I get 9 times 9, which is 81, minus 1/2 of 9 squared, which is 81, minus the lower bound, which is 0 minus 0. And so I get 81 minus half of 81, I'm going to be left with 81 over 2. So this is the volume of our tent, 81 over 2.